Just 1 second. Very good evening, everyone. Myself, Chiranjeev Sarkar, Vice Chair, Tunnel Association India Young Member Group. On behalf of Tunnel Association India Young Member Group Committee, we welcome all of you in our today's webinar on multi-layer lining design, a new framework for tunnel lining design by Dr. Jiang Su. About Dr. Su, Dr. Su has worked in the tunnel industry for more than 17 years. He is currently working as a technical director in Ramboll UK Tunneling and Underground Space Team. His project experience include Crossrail, Thames Tideway, Silver Town, Mumbai Metro, and many more. He is a chartered engineer and a fellow of Institution of Civil Engineers. He is an editorial board member of IC Proceeding Geotechnical Engineering, and he holds a PhD in Composite SCL Tunnel. So over to you, Dr. Su. Welcome you. Yeah, you can start.
Can everyone see my screen firstly?
Yeah, is it visible?
Cool. Great. Thank you. Hello everyone. Good afternoon, good evening, or maybe even good morning, everyone. I mean to the audience in the different countries in the world. And it's my great honor and pleasure to have this opportunity to give a presentation on this emerging topic on the multi-layer lining MLL line design, a new framework for tunnel lining design. And also thanks for the chairs to give me an introduction of my background. So before I come to the main presentations, I'm just spend 1 or 2 minutes talk about the Ramboll. Is kind of use these opportunities to let you know what kind of company we are. We kind of a independent architectural engineering consultancy company. It's a Danish company founded about 80 years ago. We got about 17,000 people globally, presented all around the world, including India. We're multidisciplinary consultancies. We got a bit of a revenue, almost 2 billion now. And then we are not listed company. We're kind of owned by a foundation, the Ramboll Foundation. And this is the office presence of the Ramboll, as you can see. And we actually do have a few offices presented in India. And most of them is in Europe and United States. Just for the tunneling capability, we have involved in many exciting projects, and we involved in the Farmer Belt between Denmark and Germany. You know, once built, will be the longest immersed tunnel tube. And we're also involved in some tideway in London, exciting SCL photo, as you can see. And our Indian colleagues are also working on some exciting projects in India. It's bypass around the Jammu city, and there's a bit of a weak rock tunnel. So yeah, just give you a bit of background. For my presentations, and the presentation is mainly based on an article I published middle of last year. As you can see, it's called the Tunneling Journal. It's in the June and the July issue, and with the same title. As you can see, it's free to read online. So if you find my presentation interesting and would like to know more, and you can go to their website to download the PDF files and to read. And obviously, one thing I would like to mention is that this multi-layer lining is originated from my past working experience from a spray concrete tunnel lining, but the principle will also apply to tunnel linings, you know, with let's say precast segmental lining as the primary lining, then followed by different type of secondary lining. Okay. So for today's presentation, the layout of the structure will be the first, because it comes from the tunneling, SCL tunneling. So I'm going to briefly talk about development of the UK SCL tunneling over the last 30 years almost. Then obviously I'm going to talk about what is the multi-layer lining and why it is different. And then I'm going to talk about the status of the knowledge. And then I'm going to give you a multi-layer lining example, which is based on study walked through before Christmas, and I'm going to try to publish that as a conference paper. So you will be the first group of people to see this study results before anyone else, you know. And in the end, I'm going to briefly touch on the importance of training the new generation of the hybrid tunnel engineer, and we draw quick conclusions in the end. So development of the UK sprayed concrete lining tunneling. The first use of sprayed concrete in UK was not well documented. So based on my study and some other literatures, it's probably called Mersey Tunnel back in the 1930s. It's like almost 100 years ago. But 60 years later, in the 1980s, the SCL has been widely used for carbon construction chalk for the Channel Tunnel. So it is a well-documented project because it's so big. It's between the United Kingdom and France. And the next step is a few years later, the temporary SCL has been adopted for the Heathrow Express station following the successful trial tunnel. So it is actually the first time the SCL being used in stiff clay, such as like London clay in the central of London. Obviously, it's only a temporary structure. So the tunnel engineer made some effort to improve this technique. So in a few years' time later, with probably the same place in Heathrow, but he got this Heathrow baggage transport tunnel, and they tried a part of the tunnel with a permanent spray concrete lining. As you can see, it's a step forward. Another few years, and the UK tunneling engineer made another effort trying to make a single pass fiber reinforced SCL tunnel at the Heathrow Terminal 5 because as you can see, previously they have done successfully a SCL tunnel with permanent spray concrete lining. So they were thinking, oh, maybe I don't need to put a waterproofing system and even no secondary lining, just a layer of permanent primary lining, so that if we can design and construct the lining carefully, make a perfect joints, and it will probably provide both function of stabilizing the ground as well as the satisfactory water tightness. But unfortunately, after the tunnel has been built, and I don't think it's quite important tunnel. It's probably a small tunnel. It's used for trial. And when people come back for inspections, people see lots of damp patches, a bit of water leakages. I mean, it's not too bad because it's not collapsing, but the water tightness certainly is not reaching to the expected level. So that's the reason the industry has thought about that and decided to bring back the waterproofing system and the secondary lining. So that's the reason in a few years' time later, in the A3 Hindhead Tunnel, it becomes the first use of the sprayed membrane in the UK and the sprayed permanent secondary lining above the groundwater table. And this is the figure showing over here. So it is obviously, you can see it's kind of coming back to the system with the waterproofing system and secondary lining, but we try a slightly different system. Rather than using sheet membrane, now we're using sprayed waterproofing membrane. And as a trial, like first ever project in UK using this kind of waterproofing system, they picked up a relatively low risk project, which is a highway tunnel above the groundwater table. So even you got some problems, you will not see like rainfall in the tunnel because there shouldn't be a build up water pressure. It will be only seasonal rains. Got a bit of a water seepages through the rock and come to the back of the membrane, but shouldn't build up a huge water pressure. Now, following the successful application of the sprayed membrane and the permanent secondary lining in the A3 Hindhead, and the next project is my first ever big tunnel projects, and in my eyes, the revolutionary project is called Crossrail. And the Crossrail is the first time that permanent SCL primary and the secondary lining, as well as the sprayed waterproof membrane, has been extensively used in UK, in the central London, below the groundwater table. So now is the time the sprayed membrane, this whole lining system, experience a challenge of build up water pressures, because it's below the groundwater table. So after that, is about 10 years from that 2012, and there were a few more tunnel projects, such as the Transport for London update, the bank station capacity upgrade, and also Thames Tideway projects, as well as the high-speed rail tunnels. So they are kind of adopting permanent SCL in either like for primary lining or just for secondary lining and with use sprayed membrane or not. So in various configurations. So if I come to the detail about multi-layer lining, just give you some of you might not very familiar with this composite lining, the lining system. So as you can see, this is a typical composite lining configurations. It comprises of layer of permanent SCO lining, and then you got a regulating layer, which was basically a cementitious layer using finer aggregates without any steel fiber. The purpose is to provide a nice smooth substrate to prevent any steel fiber from sticking out and damaging the spring membrane, which will be applied later on. And then the common practice nowadays in the UK is you apply the 2 layers of sprayed waterproof membrane with big contrasting color. As you can see, it's one layer is red, one layer is white, so that after the spray, because this kind of material it contain lots of water during the spray, it will evaporate the moisture, so it will generate a bit of sometimes generate a hole due to the shrinkage. So in that case, you need to kind of have a late layer, another pass, just spray over to cover these holes for the quality assurance purposes to make sure it's definitely providing the required water tightness. And following that, you just spray or even cast another layer of permanent secondary lining, as you can see. So basically, as I mentioned in the slides, and the benefits of using the spray membrane is the double bond providing limited water leakage, and also it claims it will provide some potential savings on lining thickness, which it's not the main topic of this presentation, but I can provide to you with some reference in the end. So as you can see, in the UK over the last 30 years, there was a lot happening, lots of different configurations, and how we are as an industry in the world in terms of SCO tunneling. And it's quite difficult to get a objective opinions from a third party. But luckily, I mean, in the recently held World Tunnel Congress 2022 in Copenhagen, and in one of their keynote speech, the Wood lecture, one of the SCO guru called Tom Melby, in his keynote speech, this is the slides. He was saying that the UK has took design in a new direction and took over from Norway as the innovator in terms of SCO lining configurations. As you can see, it's from mid-90s traditional double shell lining and all the way to this latest composite permanent SCO. So that's kind of it's good news for us, which means we are really we're leading in the SCO lining design, and we probably should keep going and to see whether we can make any other improvement. So okay, so what is MLL? I mean, based on what I have said over the last 5-10 minutes, and you can see that about 20-30 years ago, when we have the Heathrow Express tunnels, and we have this kind of traditional sprayed concrete lining comprising sacrificial primary lining, a layer of sheet waterproof membrane, and a layer of permanent secondary lining. It can be usually it's kind of casting steel with heavy reinforcement inside. I guess that's still the most commonly used SCO configurations in majority of the world countries in the world. And obviously, over the last 30 years, we have seen technology development. We have the permanent SCO. We now see using the sprayed waterproof membrane. And we are starting to using steel fibers, replacing steel bars in the lining. Also, we have more advanced final element analysis to help us to design the tunnel lining more efficiently. On the other hand, we have a pressure from the client and the legislative bodies in the UK, such as the health and safety requirement. We want to get a reduced health and safety risk, and we want to better use of materials and reduce the carbon footprint, and also accelerated the construction program. So combined with all this technology development, as well as the pressure from the client and contractors, and nowadays, and in the UK, the most commonly used or latest lining configuration is kind of summarized in 3 types. The first type I give the name called fully composite SCO. And it comprises a layer of permanent primary and a layer of permanent secondary lining without membrane in between. So basically, it's just direct concrete to concrete contact. So the projects that this type of lining system has been used is Thames Tidal West, and sometimes use that in the junctions between tunnels, and as well as the shaft and tunnels. Okay, I'm going to give you an example based on this kind of lining system later on. Second one, partial composite SCL is actually typically people call them composite SCL, is the one you have 2 layers of permanent lining with a layer of sprayed membrane in between. So as shown in the photos in the previous slides, it is being widely used in the crossrail, the Bond Street Station, Tottenham Court Road, Bank Station capacity upgrade. So it's kind of most commonly seen lining configuration in a London tunnel project nowadays. And the third one, I call them non-composite SCL. It's basically almost like more traditional SCL lining configuration, but using permanent primary and secondary lining with sheet membrane. So this lining configuration are mostly used in situations when the ground is a bit wet and after you build the primary lining, the substrate is too wet. You can't actually spray the waterproof membrane onto it. So it's being used in some of other projects, also in Crossrail, in some of station Farringdons, and also tidal projects, central stations, central contracts. So with all these 3 different types of linings, I call them multi-layer linings. The main difference is that they're all comprising at least 2 layers, permanent linings, with different types of interface in between. Remember, sometimes in the design, you might be designing not only 2 layers, but 3 or 4 layers of permanent layers of lining, with different interface in between. Okay. So what's this impact of this multi-layer lining in terms of design focus? If we split the traditional SCL tunnel construction into 3 stages, the first stage is ground excavation and the primary lining installation. Second stage is waterproofing system installation. The third one is the secondary lining installation. The traditional SCL tunnel lining, the most challenging and interesting part of design work, it's the ground excavation and the primary lining installation, because the challenge is to, once you excavate the ground, you need to provide the support to stabilize the ground without causing collapsing. Okay, so once that's been done, you're safe. Okay, so the rest of the work is more routine, well-established practice. It's like you basically put sheet waterproof membrane, then you probably casting steel secondary lining with shutters with quite heavy reinforcement, which was designed for overburden or very heavy load, so it's absolutely safe. So what happens when we come to this multi-layer lining SCL tunnel design? And using UK as example, over the last 30 years, there have been a lot of SCL tunnel being designed and constructed in London at least. And they almost become an established design and construction method. And 30 years ago, there probably only 1 or 2 tunnel consultancy claim that they can do SCL primary lining design. Nowadays, my understanding is that you probably got more than 10 design consultancy. They all claim they can do SCL tunnel design. Okay, so then the challenge is actually the interesting part. It becomes the second and third part is the waterproofing system and the secondary lining. For example, if we are going to using sprayed membrane or without any membrane, for example, you're just adding some waterproofing agents into our primary lining mix, and trying to achieve the same level of water tightness. And this kind of things are very interesting. And also the secondary lining is, not just put heavy reinforcement and casting screws. You're trying to do fiber reinforced secondary lining with the reduced lining thickness to achieve the efficiency in material and try to reduce the construction program cost and hence the carbon footprint. So as you can see, from the design perspective, previously the focus, more interested part is more on the soil structural interactions. Okay, but nowadays it's more structural, like primary, secondary lining interactions, and more material focused. How we can achieve the biggest efficiency, maximum efficiency of using the materials. Okay, so what's the current status of the knowledge about the designing multi-layer linings? And I have to say, you don't have that much choice because I mean, for example, some of you tunnel engineer, young tunnel engineer, and you listen to these great presentations from people in the UK, maybe from me or someone else, and they all say, "Oh, composite lining is great," and you want to design that in India or any other countries, and but you need a step-by-step guidance. So the way usually you do is you just look for some international guidance, such as these documents published by the ITA Tech Group, or some of the tunnel design guidance on the Australian Tunneling Society, and about trying to find a way to design the multi-layer lining. But unfortunately, this design guidance basically can't find any like practical step-by-step design guidance. The tips, they just give you some introduction, you know, like at a very high level, just tell you what is this composite lining is and how it works, but you still have no clue how to design that. Or another way is you can try to find some textbook or a book published by some SCL experts such as Alan Thomas or Benoit Jones. They are all UK educated, trained, great tunnel engineers. But their book are also mainly focused on the soil structure interaction in the primary lining design, and not much covering about multi-layer lining. So actually, it's my personal inspirations to probably publish a book in a few years' time, just to specifically talk about this multi-layer lining. Obviously, this is my great hope. So what's the kind of status of knowledge? I mean, as I just mentioned in the previous slides, and we don't actually have many sources of information available for the tunnel engineers to design multi-layer lining. If you read my article later on, I actually list 10 questions, and which I don't think anyone have answered publicly in any articles about the multi-layer lining design and construction as well. And I also provided some of response to that, obviously for the time limit, and I'm not going to cover all of them. I will pick up some interesting and key ones, I think, for today. There are three. The first one is the load sharing. It is quite interesting topic because if you design a tunnel with two layers of permanent lining, it's quite important to understand which one takes more load. Because previously, usually if you are designing a primary lining, a sacrificial lining, and you don't worry about this question, your secondary lining will take all the long-term load. So this load sharing issue is key for designing the tunnel. The second one is effective composite actions. 15 years ago, when I started my part-time PhD on this composite SCL tunnel, my original purpose was to try to prove the composite action is beneficial to the tunnel lining. After many years, after the study of the PhD, I actually proved that it's not beneficial to the tunnel lining, which is kind of totally opposite of the original purpose. But I guess that's the meaning of the PhD research, to identify the true engineering impact of some of this kind of engineering effects. So I'm going to briefly talk about that as well. The third one is the advanced numeric modeling. So if we're going to design any multi-layer linings, we need to use this advanced numeric modeling to realize its effect. Otherwise, we design something not real. Okay. For the load sharing, I'll give you a very quick example. Imagine you have a full perfect circular tunnel lining, and you have the same thickness, same stiffness, and you under external UDL, uniform distributed load. You have a concrete direct contact. So because you got same axial stiffness between the two layers linings, the load sharing will be 50 to 50%. That's the one extreme. Another extreme, imagine you have a waterproofing system in between these two layers. Let's say about 10 millimeters thick, by stiffness so low, you can imagine it's an air gap. So now you have an air gap in between the primary and secondary lining. And under the external ground load and the ground pressure or any loads, the primary lining only converge by 5 mil. So actually your primary lining and secondary lining are not in contact. That means your primary lining is taking 100% of the load. So what does that mean? That gives you a general idea about the range of the load sharing. It's basically if you have a reduced membrane interface stiffness, your load sharing will moving from my left-hand side example, the right-hand side example. Obviously, this is not only the impact factors to consider. If we have a different lining thickness, obviously, if your primary lining is thicker, it will take more load. And direction of the load. If we, for example, if we're designing a sewer tunnel, if we got the internal surge pressure applied inside out, and for the first scenario on the left-hand side, it still got to be 50 to 50% load sharing, but on the right-hand side case, your secondary lining will take 100% load sharing, and your primary lining will be 0. So basically, the general conclusion is the softer the interface and all the single secondary lining, the less of load in the secondary lining will take, providing the load is coming from outside. And also the load sharing is determined by the combined effects of above factors, not by assumptions, because this load sharing is so mysterious. I mean, like many people, when you designing or category check it, they don't calculate the actual load sharing. They just assume that our primary lining will take 70%, secondary lining would take 30%. Well, for their design or category check. But there's a way to do that, to actually quantify the load sharing. The second thing is composite action. So how composite action works in tunnels? I'm going to give you an example about short-term effects and long-term effects. So for example, imagine you have a SCL tunnel, those two perfect circular, but with a flat invert over here. So if you have a permanent primary secondary lining with a sheet waterproof membrane, so that you don't have any tension, okay, you can allow to separate. So after you spray or cast your secondary lining will shrink due to the early thermal and the shrinkage effects. So the secondary lining on the self-weight will develop a bit of tension, as you can see. That's the red colored part, inside of the secondary lining and outside of the shoulder of the secondary lining. But if we got sprayed membrane, because the membrane got the double bond effects, your secondary lining cannot move away from the primary lining. So that the tension will be developed at the most in most of the secondary lining. Noticeably, the biggest tension will be generated in the secondary lining crown inside and also the knee positions. So that's the reason for most of the SCL tunnels, like partial composite lining tunnels, they're usually designed as the non-composite tunnel nowadays in the UK at least. And after the construction, in the very short term, you will usually see longitudinal cracks happening on the crown. And I've personally seen this happening multiple times. And the people don't understand the reason, but that's the reason. The reason why you don't see the much cracks happening over here is because usually people cast the flat invert first, then they spray or cast the rest of the secondary lining. So we've got construction joints over here, kind of allowed to move a little bit. So it's not a big concern over there. And also they usually got this steel reinforcement connecting the flat invert and the knee positions. So that's what will happen in short term. And obviously, the higher degree of composite action, the more restraint you get from the primary lining, and the more higher tension you will get. And I will show you the example later on. What's the long-term effects? Long-term effects, even if, let's imagine, even your primary lining does not deform in the short term, okay? And put your secondary lining in the long term in London, the tunnel generally squatting horizontally. So you will see T is the tension, means the tension will develop in the secondary lining intrados and flat invert of the secondary lining. You got compression, got the access level at the intrados of the secondary lining. So again, the biggest risk is at the secondary lining crowns, because they usually got lots of tension being developed. And so basically, it's based on my study and the observations from real projects. The lower the degree of composite action, the better for the concrete tunnel linings. Third one is the advanced numeric modeling. Okay. Historically, or in most scenarios, people modeling the tunnel linings using beam element in 2D or plate element in 3D. But you can't use it for modeling the multi-layer lining, because you need the key to model the primary secondary lining in the multi-layer lining interaction is that you need to have an in-plane shear to allow to compensate action to be generated. If you look at the beam or plate element, they only got 3 force components. It got auto plane shear, axial compression tension, or the bending. They don't have this in-plane shear. So that if you stick 2 layers of beams together, or 1 layer of beam and 1 layer of volume elements together, you can't model the compensate action properly. So basically, so if someone tries to design a multi-layer lining by using 2 layers of beam element, you don't need to even look at the result. You know the result will not be correct. The advantage of using the volume element is that by using the advanced concrete nonlinear plastic models, and you can model the plasticity in the cracks. You can predict the cracks in the tunnel lining. This is a paper published in World Tunnel Congress in 2022 for real projects in London. So you can see it got high tensile stresses. This is like maximum tensile stresses, and this is the plasticity point for tension cutoff. Another real projects example is that it can simulate the shrinkage. So for example, this shows the primary lining. In this case, it's actually, in real case, it's a kind of segmental lining. And once you cast the secondary lining, we assume it will debound it, give it a bit, resulting in some gap being generated. Then you apply some construction loads. So push the lining back, close the gap. So in these scenarios, and you can see the maximum tensile stress, and you actually can calculate the maximum crack width. And this is a real case that we successfully predicted the maximum crack width up to 0.3 millimeter, and we measure that, and then also the maximum crack width, it is like 0.3 millimeter, happened only once. So it's a great success in terms of using this multi-layer design advanced numeric modeling for the real tunnel projects. So, okay, I'm going to quickly give a real example to demonstrate the power of this multi-layer lining concept, and also the using advanced modeling technique, and also the based on the understanding of this multi-layer lining to back analysis a cracking issue happened in a real projects. So this is the real projects in London, finished a few years ago, and this is a plan of the SCL platform tunnel. So basically, SCL tunnels, you got platform tunnels on the top and the bottom, which I didn't show, but this is a station box. You take an escalator coming down, you have this concourse tunnel, then you have 4 cross passage tunnels linking to 2 platform tunnels, so that and people can get onto the train. So after the construction of this concourse tunnel and the cross passage tunnels, and we witnessed on site a very obvious longitudinal cracks being developed. I mean, you can for SCL tunnels, you can see some local small cracks, no problems, and you always got a bit of a problem, material issues, imperfect workmanship, etc. But for this kind of extensive, for this level of longitudinal cracks is a big one, and people are doing drilling holes. You can see there's spiral cracks all the way through the lining, and it's quite big. So, but do we really understand it? I don't think anyone in the industry has answered these questions, and I think I discussed it with the original designers, and they still don't have clue how it has happened. So I'm going to try to explain this by using this multi-layer framework. So before I go to these kind of numeric modeling things, and just to briefly introduce the contraction sequence of the junctions. So basically, for the project, for the junction construction, you basically have first you build up a layer of primary lining, then around the openings you put some reinforcement locally around it, then you spray or cast another layer lining. So usually we call them thickening layer. So it's actually this lining. Then you break out to construct the cross passage. So the cracking happened is actually in the thickening layer, not the primary lining. So the tunnel wouldn't fall down, but still a secondary lining, sorry, the thickening layer got such big cracks. It's kind of not great, in front of the client if the client come down to visit the tunnel. And so the original design approach is to using FLAC, many years ago, 3D, to build up a parent tunnel, the main tunnel, concourse tunnel, and put the total thickness about, let's say, 800mm thick lining, and then you create the cross passages. So then you will see the stress concentration factors around the openings. Then you design the extent and the magnitude of the rebars, how far it is, and whether it's B25 or B32 reinforcement. So at that time, it is the most advanced design methodology at that time, and however, it still got a bit of shortcomings. And if you look at this design methodology nowadays, first, it did not consider the sequential construction. So basically, the primary lining in reality being constructed first, which resists all of the load, short-term load, and when we put the thickening layer, in theory, it does not take any external load. It will experience a bit of a shrinkage, self-weight, and early thermal effects, but not external ground load and groundwater pressure. And also the impact of multiple junctions was not considered. It was only considered one junctions. And obviously, as I just mentioned, the early age thermal and shrinkage are not considered. So basically, in order to simulate all these effects, we need to use these advanced modeling techniques to using volume element rather than plate element. And just to clarify that, this presentation, when I talk about the shortcomings, I'm not criticizing the original design method approach. It was I believe, the world-leading design approach at that time. But obviously, with the time passed by, we got more powerful computer, and we have better understanding of this multi-layer lining and systems. So we move to the next step. So for the numeric modeling, so basically it's a typical Praxis 3D and typical London stratification made of ground, terrace gravel, London clay, with this platform tunnel, 2 platform tunnels, this concourse tunnel, and the 4 cross passages. The tunnel lining are the pilot tunnel is modeled as a plate element, and the concourse tunnel is modeled as like volume element, as you can see. 3 models being developed to demonstrate the effects of this multi-layer lining framework. The first one is that it's almost the original approach. You don't model the sequential excavation. You just put the primary lining and the secondary layer together in one go, and no early thermal and shrinkage effects being considered. The second one is the considered sequential construction, but not the early thermal and shrinkage. And the last one is, from my perspective, is the right approach, is to consider both. Just bear in mind that this is kind of my little mini study, and just try to, the main purpose is to quantify the reason why this has happened, rather than, sorry, not quantify, qualify the reason, not give a very accurate number in terms of quantifying the contributing factors. So quickly, construction sequence, you can see firstly using volume method for TAIym construction, then you do the SL pilot tunnel and lining, then you enlarge the enlargement, put your primary lining, then you put your second layer. So this is the key stage. I will present the result at this stage. Then obviously the next one is the construction, the next 4 cross passages. Also in the end, I will present the result for that stage. So that's the 2 key stages I'm going to present the result. The first one, model 1 result, is no sequential construction, no early thermal shrinkage. As you can see, once it's being built, this is the second layer only, no primary lining, because it resists the short-term ground load. There's no tension developed, it's a pure compression. You can see it's a minus 1.5, 1.8. Even with the contraction of the junctions, the lining of the crown is all in compression. So that was the original design approach. You will get results. So you don't think you need any reinforcement in crown because it's absolutely safe. Okay, all in compression. The second one is you consider sequential construction. So basically, you put your thickening layer in the next step, in the following next step after the primary lining construction. So it does not take any external load. It's only experience its self-weight for this case, because in this case, there was no early thermal and shrinkage load being considered. You can see it will develop very small tension. It's purely due to its self-weight. Okay, but then after the construction of cross passages, you will see a maximum 1.4 MPa tension happened. Interesting point is happened between not in the crown, between the right above the cross passages, but it's in between the crown of the 4 cross passages. It's in the middle, 1.4 MPa. And if you look at that maximum tensile stress, you compare with the testing result Eurocode, it's well below. It's kind of the lowest characteristic tensile stress of corresponding C2832 SCL is about 2 MPa, 1.9 MPa tensile stress, so the crack wouldn't happen. So it's not right. So the third result is we consider both the sequential construction and the early age thermal shrinkage. For this scenario, I'm using a 300 macro strain as a trial, as first trial, because why I'm using that is because for the project specification, the 28 days shortening of the NaSCL spacement has been limited to a maximum value of 300 macro strain. So I'm putting the 300 macro strain into the model. As you can see, it got a big tensile stress. It's 4.3 and 4.8. And after the construction of the cross passages, the value is similar. Some places even reduced. But that means the lining will crack right after you construct the secondary, the second layer. It's different from our observation. Why is that? It is because when the shrinkage happens, the 300 macro shrinkage happens in real life, the shock rate will undergoing a development of its stiffness and strength. So coming from a very soft material to become very stiff material. So that shrinkage, early age thermal effects, is developed through all the process. So although it will shrink by that 300 macro strain, but the stress developed will not be that much. So that's the reason I tried. For practical purposes, we're not going to do laboratory testing for a very rigorous scientific investigation. We just do trial and errors to see what's the value we should put for this analysis. So what I found is if I put a 110 macro strain, I will generate a tensile stress, maximum tensile stress, about 1.8, 1.6 MPa, which is just below the 1.9, 2.0 characteristic tensile stress for the corresponding class grade of the concrete. So it's not cracked in theory, but then after you do the cross passages, you can see the central area, not right above the cross passages, but it's in between, will be developed a value tensile stress greater than 2 MPa. In theory, will causing cracks, but the other part will not. It's lower than 1.8, 1.9, so will not be any cracks happening. So that kind of perfectly matching of the observed cracking scenario. Okay, so then the next question is why the cracks only happens over here, not over these places. So I'll give you an explanation. This is deformation of the tunnel linings, of the thickening layer. So this bit is the head wall, the end. So you got the cross passages. When you have a head wall, because it's so stiff, it does not deform at all, a little bit. So it's still quite circular. You don't develop much bending. And for the area where you got cross passages, because of you dig a hole there, your lining, the ring stiffness is reduced. So it's kind of deformed more like a circular. It is only the middle part. You don't have a hole over there. So your stiffness is still there. It kind of do its best job to resist the external lining by deform a lot. So basically the crown bit is so flat. Everyone knows, if you have a relatively flat structure and resisting the external load, you will develop bending and rather axial compression force. So that's the reason the cracks open here. And also, if you look after review the modeling result, the maximum tensile stress is actually not only showing in the intradose of the thickening layer, it's all the way through the back of the thickening layer. That means that kind of corresponds to the set of observations that when you dig a core, concrete core, you will see the crack depths all the way through of the thickening layer. Okay. So after giving this presentation, and this is kind of important about the training the next generation hybrid tunnel engineer. As you can see, the example, If you think about historically the tunnel engineer design for soil structure interactions, most of the people engineer will come from engineering geology or geotechnical background. Okay, and not many people are coming from structural or material background. But nowadays, if you want to carry a full life cycle of the multi-layer lining design, you need to understand a bit of geology, and you can derive geotechnical parameters so that you understand the ground behavior. You can do soil structure interactions. Then after that, you need to understand the structures, like lining, like primary, secondary lining, or in this case, primary lining to thickening layer interactions with different interfaces, and also the results you got is not just bending moment, axial force. Now you get the principal stresses or strains. By using that, you need to be able to predict the crack width to see whether the lining works well or not. And also you need to understand the material behaviors, such as this early age thermal shrinkage effects, and also different membrane properties, and how to behave and between the two layers of concrete linings. So yeah, just in conclusions, a multi-layer lining is a new trend focusing more on the structural and material aspects. And currently there's no detailed design guidance. This multi-layer lining framework covers a wide range of topics. And I've demonstrated in my example that using multi-layer lining approach is able to design the tunnel lining efficiently. Well, in this case, it's kind of back analysis, to understand the engineering, the reason why it's got cracks. And last but not least, there's a need to train a new generation of the hybrid tunnel engineers. So with a slightly balanced skill set on the ground part on the right-hand side of my previous slide, and also left-hand side, the material structures, being able to do a good full life cycle multi-layer lining design. In the end, there was some reference for this. It's all mostly myself, the publications on this multi-layer lining topic framework. And if anyone got interested, and you can read and to help you to go to sleep. Thank you very much. You got any questions?
Yeah. Now we open for a question. Those who want to ask question, please raise your hand. Yeah, please. Even you can text your question in our chat box. Do anyone have any question? Yeah. I think
Great,
Mr. Ravi Shah. Yeah, please.
Hi, Jiang. Nice to
hello.
see you again.
Good to see you. Yeah.
Quick question. I've got a couple of questions, two-part question. One is like the industry is now moving towards, I think you touched on steel fibers. There are like industries moving slightly towards PP fibers. What are your thoughts on that? Because they're generally used for like fire protection design. Do you think like they can add to any structural strength? And the second one is like, could you recommend any hand calculations like to sense check the results that we get out of numerical analysis, or like
Good questions. Like thank you. To answer your first questions, the polypropylene, the plastic fibers, I mean, it's basically, I guess you know that the plastic fibers generally you can have macro structural plastic fibers and macro fireproofing fibers. So basically the macro plastic fibers has already been introduced in the industry, at least back to like 2010. It's kind of, at that time, it's kind of almost like two parallel the trend of using either go down to the route of steel fiber or go down to the route of the plastic fiber. I think one of the problems is the plastic fiber. There are two issues. One is that it's relatively less stiff when compared with steel fibers, and after testing in the long term, due to its kind of creep effects, it will elongate a lot. It loses lots of structural capacities. So that's the reason for some of the major UK tunneling projects, the plastic fiber, structural fiber wasn't being adopted. Another reason is that the plastic fiber is actually causing more environmental issues than the steel fibers. well, it's kind of not my finding or opinions. It's kind of some other governments, for example, Norway. In Norway, they realized that the steel fibers, although it's generating more carbon footprint during the production or usage, but it can be dissolved, back to the nature in, I don't know, 10 years or 100 years. But if you have a plastic fibers, if you got lots of plastic fiber not being used, and you leave them somewhere, or you bury them there, and or you leave them to water, it will not dissolve for million years. It's causing more natural damage. So actually, that's the reason I think there's a slight limitation of using the structural plastic fibers in the acetyl tunnel lining. To answer your second question, is any calculation? Yes, I think so. Basically, you will need to give example. If you design this multi-layer lining, primary, secondary lining with spray membrane, you probably need to do at least once praxis analysis and get the rough idea of the ratio. Then you can basically develop that using closed form equations. And I can't remember what the equation's name is.
Is it like
but
Dudek and Erdmann?
Yeah, Dudek element. Yeah. I actually have done this for many, back to 2016 or 17, because some of these spray membrane manufacturers asked me whether there was easy Excel spreadsheet that can roughly calculate how much the axial force and bending it will be in this composite lining system. So I developed one. So we're using Dudek element and with the proportion of the load, and it almost like predetermined ratio based on a real praxis analysis or flag analysis. Say primary lining takes 70%, secondary lining takes 30%, something like that to do that. So that's kind of hand calculation. If that's what do you talk about? What do you mean? Hand calculation.
Thank you.
For stance check. Yeah, for stance check. Yeah.
Anyone have any question? Yeah. Yes.
Yes, I can
please,
ask a
please.
question. Thanks for a great presentation, Jiang. I have a question regarding this waterproofing.
Yes.
What was your experience in terms of the performance of sprayed waterproofing compared to membrane? Is it
compared to sheet membrane?
Which one you prefer? Let's say start that.
Yeah, you mean the sheet membrane, right?
Yes.
The spray membrane compared with the sheet membrane.
Correct.
I think. Yeah. Okay, great. Good question. Thanks. My opinion is that sheet membrane is more easy to apply and kind of more reliable if you don't have very high scale of operatives to apply the sprayed membrane. Sprayed membrane can significantly reduce health and safety. For example, you don't need people to go up to the crown to welding things, and that's a big plus. But the problem is that because it's such a new thing, and there are not many experienced, skillful nodal men or sprayers to apply that membrane, and also sometimes the contractor, when they do the constructions, they kind of trying to achieve fast construction. So before the sprayed membrane because I must have mentioned that most time it will spray in 2 layers. I have witnessed in my professional career once that we specify the first layer of the membrane needs to be dry enough, then you can spray the second layer. But the contractor just wants to speed up things, so before it's being fully dried to the right level, they spray the second layer. So end up with, in the back of the primary lining, you don't have much permeability because you got this permanent, perfect SCO primary lining. Then the inside, you got this second layer, which is with the purpose of waterproofing. So the pool, the first layer, the middle layer, first layer of spray membrane is kind of still wet, but have no path to dissipate or get the moisture out. So end up with, like, after another 2 weeks, it's still not sticking because it's not queuing, it's not evaporate the moisture. So basically, my understanding is that it will be if you don't have a reliable, experienced, skillful operatives to apply waterproof membrane, you better using sheet membrane. But if you have the resources, and if the tunnel designer is clever enough and experienced enough, they will provide a better solutions, more economic solutions. I'll give you a real project example. I mean, when I was in my previous employees, and I worked on one of these Mumbai Metro, and I think it's the Mumbai Metro Line 3. I think it was a big canvas. The original design was the traditional SCL in the sheet membrane, B22, B20 bars, 2 layers. I mean, casting steel secondary lining, heavy reinforcement. And we were brought in and we changed the design to spray membrane. We changed that for the arch. Majority of the secondary lining is the fiber reinforced concrete, and only the invert we got a bit of reinforcement, so that you can see that by doing the design change, you can actually make lots of savings in terms of cost, program, health and safety. Yeah. I hope I answer your question.
Yeah, no, thank you very much.
Yeah.
Anyone? Yeah, Shohel, please.
Hi, Jiang.
Hello.
Hey,
Hi.
Regarding a TAIym Tightweight tunnel, you said that you used permanent primary and permanent secondary membrane without any membrane in between.
Yeah, we used the TAIym West project. You got paper actually published. It's the this one. It's the permanent primary lining and the permanent secondary lining direct concrete to concrete contact.
Okay, so there was no requirement of waterproofing membrane over there.
That's I slightly mentioned the touch, and I didn't emphasize that. That's the reason they added a product called Cypex. Is a liquid. I think it's a liquid additives. You added them into the primary lining concrete mix. So
Okay.
it says it will, once it got cracks in the lining, it will crystallize itself to fill the voids. And so that has been a big innovations in the TAIym West project. So the design purpose is using the high performance permanent primary lining, which is already supposed to be watertight. Then also plus this Cypex, like water tightness agent, to provide like almost like 2 layers barrier to the water for the water tightness purposes. I think if you search on Cypex website on Google, something like that, on their website, I think they said that they've been used in TAIym West. Yeah.
Okay, so means is it was like a self-healing sort of concrete that you were telling that if it cracks happens that it will crystallize, something like that, if I'm getting it correct?
Sorry, can you repeat your question?
Means you said na, if the cracks happen in concrete,
Yeah.
the material you use it,
Yeah.
it will crystallize. So it's like a sort of self-healing technique would be like that.
Yeah, almost like that. I mean, for the I think self-healing is got a limit about 0.3, 0.4 millimeter crack width, I guess. That's my understanding. I don't know the detail about whether it will that agent Cypex can be able to fill even bigger crack width for the water tightness purposes. But it's something similar, yeah.
Okay, thank you.
Yeah, thank you.
Any more question? I think we don't have any further question. Okay, yeah. If anyone have any further question, you can contact to us. We will definitely forward your query with Dr. Su.
Thank you very much. Yeah.
Thank you, Dr. Su, for a wonderful webinar on multi-layer lining. I'm sure that your experience will be helpful for everyone, and hope our student members have got a clear idea on our today's topic. I would like to inform that all of our webinars are available in our YouTube channel, and this webinar also will be uploaded very shortly. If you are not a member and want to become a member, so kindly contact us for detail. So before signing up, I would like to request all members to renew their membership for the year 2023 to ensure timely benefit. I would also like to invite new members to be part of Tunnel Association India Young Member Group for solely focus on bridging the experienced professionals working in different projects, and also act as a platform to share technical expertise in the field of underground construction. And there are always many additional benefits of being a member. So grab a chance to bring it one. Once again, thanks, Dr. Su, for
Kiran.
sharing your experience, and thank you all for joining. Have a great weekend. Stay safe. Happy tunneling.
Chiranjeev,
Yeah.
just sorry to bother you. I think there's a question hand raised from Constantinios. I think
Okay.
if he has a question, I think he can go through.
Yes,
please.
please. Just a final question. Thank you for your great presentation. I
you.
would like to ask what's an average Young's modulus of the sprayed waterproof membrane from commercial spectrum, and if the bond strength between the sprayed waterproof membrane and the concrete linings would be quantified. I think I know ATA suggests like a 0.5 MPa. Do you agree with that? That's two questions.
Yeah, thank you for your questions. Okay, that kind of like open big topic, which I can probably talk for another 1 hour, but I just quickly answer to you. The direct answer is that the sprayed membrane itself, and you shouldn't look at the membrane, the Young's modulus itself, because it works within a sandwich structure, composite structures, and is heavily influenced by the boundary conditions. It's like almost like imagine it's a kind of traxial test environment or confining stresses from the top and bottom and all surrounding area. So by doing the testing on the membrane itself, it will know you kind of underestimated the result, and so that's the first reason. The second reason is that the membrane status, the dry and the wet membrane, in the short term and also in the long term, the value you can have 4 different values, and I can give you the values which are being published on my papers and on this for this values. And the third one is I think when you talk about 0.5 MPa, it's kind of general understanding that when you apply the spray membrane onto the primary substrate when the membrane is still dry, and when you do this dolly test, you can pull away that to make sure they got the tension bound at 0.5 MPa, which is necessary or needed for ensuring the spray membrane is bonded to the primary lining substrate in a very short term. But actually in the very long term, and I didn't mention in that as this one, as I recently actually published a paper on this topic, because actually when you in the real tunnel scenarios, when you have water pressure applied onto the extract of the membrane, your membrane will under compression, but your membrane, the interface between your membrane and the primary lining will under tension. So it is that interface pressure in the long term when the membrane is wet is very important. And I'm currently doing a research collaboration with the University of Cambridge specifically for this question, and we got first proof testing results, and the interface and tension is above 0.5 MPa in the long term. So to answer your questions, I think 0.5 MPa is almost like a minimum to ensure that in the long term the membrane and the primary lining will stick together under the water pressure and also when the membrane becomes wet. I hope I have answered the question.
Yes, thank you very much for your analytical answer. Thank you very much.
Yeah, thank you.
Any question, or we'll close this session? Okay. Thank you once again, Dr. Su, for today's amazing presentation. So everyone, have a great weekend. Stay safe. Happy tunneling. Thank you.
Thank you.
Thank you.
Bye.
Have a good weekend.
Bye.
Bye. Bye.